Hi students, today we have discussed about the functional analysis in the section continuous linear transformation. Already we know that the definition of continuous in real analysis. So that is the same way we have discussed about the continuous linear transformation in normed linear space. So let us consider n and n dash be the normed linear spaces with the same scalars, and let t be the linear transformation on n to n dash. T is continuous if xn converges to x in capital N implies that t of xn converges to t of x in n dash. This is the definition of continuous linear transformation. Next, the following theorem is equivalent to the continuous linear transformation. Okay. Now consider normed linear spaces n and n dash, and t is a linear transformation from n to n dash. Then the following conditions are equivalent. The first case, t is continuous. Second case, t is continuous at the origin. That is, xn converges to 0 implies t of xn converges to 0. And the third case, there exists a real number k greater than or equal to 0 with the property that norm of t of x is less than or equal to k into norm of x for all x belongs to n. And the fourth case, if s equal to set of all x such that norm of x is less than or equal to 1 is a closed unit sphere in n, then its image t of s is bounded in n dash. Now we prove that 1 equivalent to 2. That is a necessary part. Let us assume that t is a continuous. Then we prove that t is continuous at the origin. Okay. By the definition of continuous, we know that xn converges to x implies that t of xn converges to t of x for all x belongs to n. In particularly, we put x equal to 0. Then we have xn converges to 0 and t of xn converges to t of 0 for all x belongs to n. This implies t is continuous at the origin. And converse part. Now let us assume that t is continuous at the origin to prove that t is continuous. So we have the definition of continuous at the origin. Xn converges to x implies that xn minus x converges to 0. Let us consider the transformation t of xn minus x is converges to 0, and inner product t of xn minus t of x continuously 0 converges to 0. Therefore t of xn is converges to t of x, which implies t is continuous. Next part, 2 implies 3. So which is also 2 implies 3 is a necessary part, and 3 implies 2 is a sufficient part. Now we have choose the sufficient part. For if any real number k such that xn converges to 0, which implies t of xn converges to 0, because xn is a sequence of number that is continuous at the origin, and 2 implies 3. Let us assume that there is no such k. For each positive integer n, we have find a vector xn such that t of xn is greater than n into xn. And we know that norm of t of xn divided by n into norm of x is greater than 1. and let yn equal to xn divided by n norm of x naught. That is yn converges to 0, therefore t of yn is converges to 0 by t is a continuous linear transformation. Next case, 3 implies 4. A non-empty subset of a normed linear space is bounded if and only if it is contained in closed sphere. And 3 implies 4. For any if norm of x is less than or equal to 1, then t of x is less than or equal to k. 4 implies 3. We assume that t of x is a normed linear space with the closed sphere where k is any real number. If x equal to 0, then t of x equal to 0, and easily t of x is less than or equal to k into norm of x. If x is not equal to 0, which implies x divided by norm of x belongs to s, and therefore norm of t of x which is divided by norm of x is less than or equal to k. Therefore norm of t of x is less than or equal to t into modulus case. So this is derived the equivalent theorem for continuous linear transformation. Next, the definition of bounded in functional analysis. Let us consider t of x is less than or equal to k into t of x, and for every variable x belongs to x, and k is called a bounded for the linear transformation, then it is called a bounded linear transformation. We consider the remarks. If t is bounded and is connected, then it is continuous. And next definition, if t is continuous, then we define norm of t equal to supremum of t of x such that modulus x less than or equal to 1 and n not equal to 0. Then norm of t equal to supremum of norm of t of x such that x norm of x minus 1. So these are the definitions. So இது free timesல கொஞ்சம் prepare பண்ணிக்கோங்க. Okay, thank you.